Hi everyone, welcome to AI Crack channel. This is Akash Ingwar and today we'll be studying definite integrals lecture 3. So this is the last lecture of definite integrals and we'll be studying property number 7 over here, which is based on periodic functions, and we'll be studying Leibniz theorem and also limit of a sum. So let's start the lecture. So before discussing the property number 7, which is based on periodic function, let's see on what concept this is based on. So let's say we have a function fx equals to mod of sine x. Let's say this is our function. And if you are going to plot this function, then it would look something of this sort. Maybe I'll plot it over here. So basically this would look like something of this sort. So this is pi, this is 2 pi, this is 3 pi, this is 4 pi, this is 5 pi. And with the symmetry, we can see that areas of all these cycles is same. So basically this area is same, this area is same, this area is same. Every cyclical area is exactly same because of the symmetry, right? Now, how can we utilize to find out the integrals or simplify the integrals? So let's say if I want to calculate the integral of mod of sine x dx from, let's say, 0 to 4 pi, I can clearly see that this is the area which I need to calculate. And with the help of symmetry, I can say that this area is exactly same as this area, this area is exactly same as this area, and this one is exactly same as this one area. And so I can do this 4 into area of one single cycle, let's say A. So 4 into A is the final answer. And what is A over here? A is nothing but 0 to pi mod of sine x dx, right? So what I'm actually doing, multiplying 4 over here. So basically my main purpose to understand with this property is I want to reduce the entire format into this kind of format. So basically calculating the area of one single cycle and multiplying the number of cycles over there to find out the entire area, which is nothing but integral, right? So this is what we are doing in the property number 1 over here. So we have n cycles over here from 0 to nt. So basically t is the period of this periodic function, and we are going n cycles towards n cycles multiplied by t. So we have just taken n outside and we are integrating from 0 to one single period of this entire integral. Same thing which I have done explained over here, right? Now similarly, let's try to understand the second property. So this was done. So this was understood based on the cycles. Now let's try to understand the second one. So in this case, we are going from a to a plus nt. Again, similar kind of thing. Let's say this value is a, this distance is a, and we are going n cycles after a. This is what this means, right? We are going n cycles after a. So from here to here, this is one cycle. From here to here, this is another cycle. So this is one cycle. This is one more cycle. This is one more cycle from here, right? So let's say we are going for the third cycle. So eventually we are calculating only three cycles. So if we are going from A to A plus NT, we are going just n cycles, and in this case, specifically three cycles. So how to understand it graphically? So what I'm basically doing over here, I have to calculate this area, right? And this one, I have to calculate this area. So what I can do, I can just, cut this small piece from here and plug it in over here, and that would give me three complete cycles. So again, to make this simpler, what I'll do, I'll remove this a, I'll take this n outside and I'll write n times 0 to t. But this is only possible when both of both upper limits and lower limits have a and a plus nt. If it is a and this is b plus nt, then it's not possible. So how to derive a formula for the same, how to make a formula for the same? So basically, upper limit minus lower limit divided by period, that would give me the number of cycles multiplied by one single cycle. So over here as well, nt minus 0 divided by t. So this would give me the number of cycles for which we have to calculate the area or integral multiplied by one single cycle area, that is 0 to t fx dx. Similarly over here, upper limit minus lower limit, that would give me a plus nt minus a, that would give me nt divided by t multiplied by one single cycle area. Again, similar thing. Similarly over here as well, you can use the same logic. nt minus mt divided by t multiplied by one single cycle area. So this is one single cycle area, this is the number of cycles, and multiplied by this one, right? So all these properties are more or less same, just the interpretation and representation are a little different. But if you understand this particular diagram, if you understand this logic, then you won't have to remember these properties. You can use this particular logic to derive them there itself and use them to finding the answers. So let's try to look at this question. We have minus 1 to 2 e raised power fractional part of 3x. And we know that fractional part function is a periodic function. So basically the graph looks like this one. I'm talking about fractional part of x. This is fractional part of 3x. I'm just talking about fractional part of x. So this is 1 again goes here. Sorry. This is 2 again like this. This is 3 again like this. Now, in case if this is 3x, then this value would be 1 by 3, 2 by 3, 3 by 3, that is 1, right? This is how the graph would look like. So in this case, we can clearly see that the period is 1 by 3. So basically, in every a cycle, the cycle is repeating after a period of 1 by 3. So what I can do, I can write this as minus 3 times 1 by 3, and this is 6 times 1 by 3. So basically we have 9 cycles over there, that m minus n formula. So we have 9 cycles over here, and we have for which we have to find out the area multiplied by e raised power fraction part 3x. Now I'll simplify it in the cyclical format. So that would give me 6 plus 3 times 0 to 1 by 3 e raised power 3x. Now, from 0 to 1 by 3, we can see that this is nothing but this fraction part 3x is as good as 3x because it's a linear function in this particular range. So that would become e raised power 3x only. And then it becomes a standard integral. 9 times 0 to 1 by 3 e raised power 3x dx. So this is how you have to utilize this periodic function property. Now let's look at this example. Now I can see that we have sin x over here and it has a period of 2 pi. And there is no trick over here in this particular composite function. So basically this entire composite function will also have a period of 2 pi only. So now we know that the function has a period of 2 pi. So what I can do, I can write this as 1000 times 2 pi from 0 dx divided by 1 plus e raised power sin x. So that eventually becomes 1000 times 0 to 2 pi dx upon 1 plus e raised power sin x. Now, whenever I see this kind of format, 1 plus e raised power x, 1 plus e raised power sin x, and a possibility to generate a negative sign over here without changing anything, then that is a very beneficial sign because in that case, we add both the i's and that gets cancelled out. So in this question, what we'll be doing, we'll be using that f of a plus b minus x property, and let's say this is our I, and I would be again 1000 times 0 to 2 pi dx divided by 1 plus e raised power sine of 2 pi plus 0 minus x, right? That is sine 2 pi minus x. That is nothing but minus sine x, right? So now this becomes 1 upon e raised power sin x only because e raised power sine of minus sin x would be 1 upon e raised power sin x. This goes with the LCM and this goes to the numerator. So this becomes I equals to 1000 times 0 to 2 pi and e raised power sin x dx divided by 1 upon 1 plus e raised power sin x. Now you can add both of them and this gets cancelled out. So eventually this becomes very easy, right? Now let us look at Leibniz rule. So if fx is continuous, then d by dx of this function equals to f of hx dot h dash x minus f of gx dot g dash x. So this is called the Leibniz rule, and we just have to remember it, and we don't have to derive it. We don't have to do anything else with it. We just have to remember it and apply in the formulas in the questions basically. So let's try to see the application of this particular formula. If fx equals to integral e raised power 2x e raised power 3x t dt divided by ln t for x greater than 0, find the derivative of fx with respect to ln x when x equals to ln2. And these are the kind of questions we are going to get in Leibniz rule. Very straightforward, not a complicated one. So let's try to do this one. So we have to find the derivative of fx with respect to ln x. So they have tried to include two concepts over here. So basically, they are doing d by dfx of d ln x. So which we know that eventually becomes d of fx by dx divided by d of ln x by dx. So basically we have to differentiate this function with respect to x, and we have to differentiate ln x with respect to x, and then we have to divide both of them. So let's try to differentiate this function with respect to x. So in that case, we know that we have to apply this limit over here. So that would become e raised power 3x divided by ln e raised power 3x multiplied by derivative of upper limit. That would be 3 times e raised power 3x minus lower limit. Will be putting lower limit in this function. So that would become e raised power 2x divided by ln e raised power 2x multiplied by 2 times e raised power 2x, right? So this is the application of Leibniz rule, and we have calculated f dash x. Now let's try to simplify it further. So this would eventually become 3x only, because 3x will come out of the power, and ln e is nothing but 1. So e raised power 3x divided by 3x dot 3 dot e raised power 3x. This gets cancelled. Minus similarly e raised power 2x divided by x dot e raised power 2x. So this would eventually become e raised power 6x minus e raised power 4x divided by x. Now we have to differentiate ln x also with respect to x. So that would be 1 by x. So basically we have to divide 1 by x over here as well. So this gets cancelled out. So eventually it becomes e raised power 6x minus e raised power 4x. And we have to apply this when x equals to ln 2. So let's do that. So that would give me e raised power 6 times ln 2 minus e raised power 4 times ln 2. So this goes over here and this goes over here, and this becomes 2 raised power 6 minus 2 raised power 4. So 2 raised power 4 is common, 2 square minus 1. So this is nothing but 3 only. So 3 multiplied by 16. 48 is the answer. Right? Now let's study the last concept of today's lecture, that is limit of a sum. Let's say we have a curve like this, and these are the points A and B, and we have to find out the area of this particular curve, right? Now what I'll be doing, I'll be dividing this entire area into rectangles, and we'll be finding out the area of approximate area of this particular curve. But again, the problem is that is the approximate area, and we'll be leaving out gaps like these, and we don't really want to leave out the gaps to calculate the final area. So for that, what we'll be doing, we'll be reducing the width of these rectangles in such a manner that they become infinitesimally small, and we get the accurate area by applying the limit over here. So this is our last, and this goes till last, and these are the approximate rectangles. Let's say this width is h. We know that h is very small, and to find out the height of this particular rectangle, so this would be f of a, right? Because this is the point a, and this height would be f of a. Similarly for this rectangle, sorry, for this rectangle, height would be f of a plus h. Similarly for this one, height would be f of a plus 2h. And similarly for this one, height would be f of a plus n minus 1 h, where n is the number of rectangles we have drawn. So n is the number of rectangles. N is number of rectangles. So this is n minus 1. Okay. So again, we can have one relation from here, that overall width is b minus a, this length is b, this length is a, so the overall length is b minus a. And if I divide by the number of rectangles, that is n, then we'll get the value of h, right? So this is n, this is h. Okay, so this is the one relation we have got. Now we have to find out the entire area. So let's try to do it over here. uh, So area of the first rectangle would be h times f of a. area of second rectangle would be h times f of a plus h, and the last rectangle would be h times f of a plus n minus 1 h, right? So this is what we have written over here. H is nothing but b minus a divided by n. So we have replaced h with b minus a divided by n, and we have taken h as common from everywhere. So that becomes fa plus f of a plus h plus f of a plus n minus 1 h, right? So this entire formula is clear for the integral from a to b, right? Now when we are making these rectangles infinite, so h will become, infinitesimally small, and we'll get the accurate area. Now let's look at one special case where a equals to 0 and b equals to 1, and we'll further extend it towards b equals to any number, but let's start with a equals to 0 and b equals to 1. Now if I do that, what will be happening? This becomes 1 and this becomes 1 by n. So basically over here h equals to b minus a divided by n. But b minus a is 1 only, because b equals to 1, a equals to 0. So this becomes 1 by n only. So h becomes 1 by n. So this formula will reduce to limit n tends to infinity 1 by n. This would become f of 0. This would become f of 0 plus h, and h is nothing but 1 by n. Third number would become 0 plus 2 by n. Similarly, f of 0 plus n minus 1 by n. This becomes the formula. I can also write this as 0 plus 0 by n, right? Now I can see that this number over here, this number over here, this number, this is the variable number. So I can write it as 1 by n sigma r starts from 0 and goes till n minus 1, and the function is f of r by n. So r starts from 0 and r goes to n minus 1 divided by, and over here 1 by n, limit n tends to infinity, right? So this is how we have written the integral now. But this is the only special case for b equals to 1 and a equals to 0. Now what if b equals to 2? In that case, what we'll be doing, will be extending this entire summation to 2n numbers. Over here we have been, taking this summation till n minus 1. In that case, we'll be taking it to 2n minus 1, right? So this remains the same. If the b minus a would become 2, and over here we'll have 2n, because the number of columns have increased. Over here, the number of columns were n. In this case, number of columns would be 2n, but we also have b minus a, that is 2. So that would eventually become 1 by n only. So even if we have a different kind of case, a equals to 0, b equals to 3, in that case we have 3n over here, and the numerator would be 3 only. So eventually it will become 1 by n only. Now what kind of conclusions we can draw from here? So this is basically our integral a to b fx dx. Now the important thing to observe over here is dx is being replaced by 1 by n, x is being replaced by r by n, and these limits. So basically a is being replaced by 0 and b is being replaced by n minus 1. So which is close to n only, because for n, when n is approaching infinity, n minus 1 is as good as n only. So b is approaching, so b is replaced by n, right? So these are the kind of transformations or reverse transformations we have to do in case of converting summation to integral. Okay. So let's look at one example to understand this one. So over here, I can see that this is written as sigma. If I take 1 by n is common, let's take 1 by n is common first. Then this becomes 1 upon 1 plus 0 by n, 1 upon 1 plus 1 by n, plus 1 upon 1 plus 2 by n, and 1 upon 1 plus 3n by n, right? So this is how this entire summation has been written. Now I can write this as sigma, and this 1 by n goes over here, and limit n tends to infinity. Now our r equals to 0, 0 over here, and r is going till 3n, and this function becomes 1 upon 1 plus r by n. This is the function. Now what I have to do, I have to change sigma with the integral. I have to change 1 by n with dx. I have to change this r by n as x. So that would become 1 upon 1 plus x. This limit would 0 and this limit would become 3 because divide by n also. This limit is going till 3n, but in actually, if we talk about b minus a, this limit would have been going to from 0 to 3 basically. So this would become 3. So this is how we have to convert the entire summation into integral. Now this becomes very simple. This is a standard L integral, right? So whenever you see these kind of questions, you have to convert them into integral format and calculate the answer very easily. So today's lecture for definite integrals was till here only, and this is the end of definite integrals. And we have covered a lot of things in definite integrals. They haven't asked these kind of questions, in-depth questions in definite integrals in the PGDB examination, but we have covered all sorts of concepts. And mostly you'll not find anything else apart from these kind of concepts in the actual examination. Very easy questions actually. Uh, we haven't covered the area under the curve yet because that is a very small topic that would just take 15-20 minutes. So I'll be covering that up later because I don't want to spend time for that kind of topic as of now, because more important topics are lined up like straight line, circles, quadratic progressions. So we'll be covering the important topics first, and then we'll be going for the non-important topics afterwards, right? So yes, let's meet tomorrow. Thanks for watching.